Hey everyone, welcome back. In this video, we're gonna talk about different type of errors that we may have on the CAN bus. So you already know that we have many videos on the channel for diagnosing the CAN bus, LIN bus, K-line, but different type of errors that we may have on the CAN bus can make it really confusing for diagnosing. For example, what you see here tells us different type of errors, including CAN bus off, CAN bus timeout, CAN bus message error, CAN bus length error, and CAN bus delayed error. So this can be all different type of errors that can happen on the CAN bus, but of course we need to know which one of these faults can be inspected and can be repaired by us. Generally, between all different type of errors, we have these three types that we can inspect and repair. The last two errors that we have here are CAN bus length error, which is referring to an incorrect length of a message on CAN bus data frame, and delayed error is referring to a message which is already delivered but with a delay, not right on the time which was required. These two errors are related to the CAN bus data frame or CAN controllers inside the control units. So basically we cannot do so much about these two, but for the first three, of course, we can do something for them. We can go for inspecting the car, inspecting the network, and diagnosing them. And these three are CAN bus off, CAN bus timeout, that I'm pretty sure you've seen these two a lot of times, and CAN message error that you will get in different format that I will explain shortly. So in this video, we're going to focus on these three to see what they actually are, because for any diagnosing, we need to have proper understanding about the nature of the fault. Then we can proceed for the diagnostic. So in this video, we're going to talk about these three type of CAN bus errors. And of course, we're going to do some practical on the car as well to see what's going to happen if we have CAN bus off and how we can proceed for finding the main cause. Before starting the video, if you guys haven't subscribed to the channel yet, please don't forget to subscribe to get the notification when we upload new videos. For supporting us, you can like the video and share it with your friends. And if you're interested to learn more about the automotive network, you can find our online courses in the video description or the first comment down below. Okay, let's start by CAN bus off. So what you see here is a simplified version of CAN bus communication network. So we are talking about the high-speed CAN bus, which is the most common network in cars. If you have watched the other videos about the CAN bus, you already know about the CAN bus, how CAN bus works, and how we can proceed for the diagnostic. If you haven't, you can find the link for some of them in the video description. But very quickly, in simple words, CAN bus consists of a pair of twisted wires, and many control units are connected to this network to share the information. This is going to minimize the wiring and it's going to increase the data transfer rate. As you see here, we have these control units like engine control module, transmission control module, ESC for brake system, electronic parking brake, electronic power steering, and so on, which are connected to the main CAN bus. But what happens when we have CAN bus off? What really happens in the car? Basically, CAN bus off DTC is the error code generated when a controller cannot transmit and receive data through CAN communication line. Each CAN controller has a feature that can count transmission and reception error. If a controller detects bus off status, it resets within preset time and restarts communication. If communication restart process continues over 10 consecutive times, the controller generates bus off DTC. If CAN bus off DTC is generated due to communication failure counter accumulation, then the controller stops data transmission and reception. This is very important. But if the network is restored, message transmission is restarted immediately. If we focus on the ECM, engine control module, if ECM cannot transmit any data on the CAN bus, it's going to detect the transmission error, but it's going to keep trying. It's going to reset the communication. But if this problem keeps happening, ECM will set the fault code and is going to stop the data reception as well. In this case, ECM itself will set a fault code as CAN bus off. This is one example that I provided for you. On the ECM, you will have U0001 CAN communication bus off. But you need to remember that in this case, ECM has some issues transmitting data on the CAN bus, and it's going to stop the data reception as well. It means there is no data transfer between ECM and other control units. And when you hook up the scan tool to read the fault code from ECM, your scan tool is going to be part of the CAN bus network. What you see here is representing the scan tool. So scan tool is going to try to read the fault code and the data from ECM, but ECM has already stopped the communication. So it means your scan tool cannot communicate with ECM. So this fault code is there, but your scan tool cannot read it right now. But later on, when you fix the car, when you connect the scan tool, you see this fault code as a history fault code that you can erase it. Some control units are connected to the CAN bus for sharing the data, and they are connected to K-line as well to communicate with the scan tool. On those control units which communicate with the scan tool through the K-line, when CAN bus is off, your scan tool will communicate and you can read the CAN bus off fault code. But what about the other control units? I have listed some other faults over here for you as well. In this case, that ECM is not communicating with other control units, the other control units are going to set a fault code as timeout or lost communication with that control unit. For example, here, this fault code on transmission control module U0100. This fault code is the lost communication between TCM and ECM. It means TCM does not have any communication with ECM anymore. Same story on the other control units. C1611 can timeout EMS. EMS represent the engine management system. Brake system doesn't have any communication with ECM anymore. So in this case, the symptom on the car could be different. You might have no starting at all. So when you connect the scan tool to read the fault code on the ECM and you get no communication, it's really important to read the fault code from other control units as well. But there is something important, because we should not consider any no communication as a fault on the CAN bus. Sometimes ECM is not communicating because ECM has some other type of issues, like the power supply on the ECM is not provided. So ECM is not communicating because it does not receive power supply. So you need to check the power supply on the ECM. Sometimes the problem is the ground on the ECM or the connector on the ECM. So you need to keep it simple at the beginning. Just go for something very simple to check the power supply, grounds, and the connector on the ECM. If they are provided, we can proceed for the CAN bus diagnostic. And this is not only for ECM, this can happen for any other control unit. So in this case, we will have no communication with only one control unit. On some cars, ECM and TCM, they are integrated in one unit. So you have powertrain control module, which is actually engine and transmission control module. So in that case, you will have no communication between those two control units because they are integrated. But please remember, this happens if there is any issue with that control unit itself, the connector, or if there is something like open circuit on the CAN bus network. If there is any short circuit here on the CAN bus line, for example, if this CAN bus line is shorted to ground, it can reflect the issue on the entire network and it can bring the entire network down. If we have open circuit in here between ECM and the connection to the main network, we will have this issue exactly. ECM will not communicate with other control units. But if any of these two wires is shorted to ground, or if these two wires are shorted to each other, it's going to bring the entire network down. And when you try to communicate with these control units using your scan tool, you see there is no communication between multiple control units. That's what we have in here. In some CAN bus off situations, you will have no communication with multiple control units. We're going to try this one and the previous one on the car. I'm going to show you the actual faults on the car. So we start by diagnosing the network by multimeter, and I'm going to show you how any of these faults can affect the waveform on the CAN bus. So if you are using an oscilloscope to diagnose the network, you will see what are the differences between a good and bad network waveform. In this case that we have CAN bus off and you will have no communication with multiple control units, the problem could be because of faulty controller, CAN line battery short circuit, or CAN line ground short circuit. Sometimes we have both CAN high or CAN low shorted to the ground. Sometimes we have CAN line open. This can happen on the wiring or sometimes on the joint connector that I'm going to show you very shortly. Or sometimes the problem is so simple, it's just because of the connector. Bad connector, corrosion in the connector can cause these kind of issues. Let's have a look at the wiring diagram before going on the car to do the diagnostic to see what is the best strategy to do the diagnostic. So this is the CAN bus network wiring diagram for that car that we're going to use for today's video. On this diagram, you see two different type of CAN bus networks. If you look at here, you see C CAN representing the high speed CAN and B CAN representing the low speed CAN. In this video, we're going to focus on the high speed CAN. For B CAN diagnostic, we have a full video on the channel. On each unit connected to the CAN bus, you see two wires. For example, here, two wires on the ECM, two wires as well. These two wires are called as CAN high and CAN low. Even these units at the top, the reason that you see one wire because the wiring diagram wanted to show you the CAN bus terminating resistor as well. So for example, you see ESP control unit here and on the other side as well. On the left side, you see the CAN low, and on the right side you see the CAN high. But of course, it's really clear that on each one of them you have two wires. One wire is shown here, one wire is shown here. And your scan tool is going to be part of the CAN bus as well. These two wires are going to go to pin number 6 and 14 on OBD2 connector. And that's a good point for diagnosing the CAN bus, of course. So this is how each control unit is connected to the network, and joint connector is going to make it easier. So you see ECM is connected to the network through the joint connector. I will show you this joint connector because this can be actually one cause of the CAN bus off. So if there's anything wrong on the joint connector, it can reflect the issue on the CAN bus. But it's going to make it easier for us to diagnose as well. Let's go on the car. We're going to try checking the CAN bus with multimeter and then with oscilloscope in normal and faulty situation. I have my scan tool connected to the car, and oscilloscope is ready for this diagnostic as well. But first of all, I'm gonna go for reading the fault codes. I have created a short to ground on CAN high, and right now we're gonna go for checking the car to see what's gonna happen when there is a short to ground on CAN high. Not on both wires on the CAN bus, only on the CAN high. So the scan tool is just trying to read the VIN number right now. Normally this scan tool reads the VIN number on this car very quickly, but as you see, it's taking longer right now. And it was because of the CAN bus issues. So I'm gonna skip this one. Let's go back to check the car manually. It's a Kia 16 pin. So if we go for auto search, again it couldn't detect the car. Let's go for manual. So right now here we're gonna scan the systems to see what systems will be detected by the scanner in case of having CAN bus off. ECM, you see it couldn't detect the ECM. Transmission, again no communication. Nothing for ABS, even airbag, aircon. BCM is different. BCM is communicating with the scan tool through K-line, so that's why BCM communicated properly. Electric power steering, nothing. And this car doesn't have TPMS. EMO, again EMO communicates with K-line, so the only units communicating are these units which communicate with the scan tool through the K-line. Right now I'm gonna turn the ignition switch off, and at this moment that we have the CAN bus off, let's see what sort of information we're gonna get from here, because I told you that I've made the short circuit on CAN high, but we're gonna go for a try it here to see how we can identify it. Ignition switch is off. I use a multimeter. You can check the resistance. I'm gonna put it on continuity because at the same time I can read the resistance and I can check the continuity as well. on OBD2 connector pin number 6 and 14, which are these two pins, these two, they are for the CAN bus, and they are CAN high and CAN low. So these two wires which are twisted at the back, you see that, they are for the network. The red one is CAN high, the blue one is CAN low. Of course, the color code can be different on different cars, because right now that we have CAN bus off, the problem could be short to ground on each one of these wires or short to each other. We're gonna go one by one for checking the continuity between each wire and ground. So if there is any short circuit, we will find it out. And we're gonna check the continuity between each one of these two wires. I'm gonna start by CAN high. I put the multimeter red probe on here on CAN high, and the black one on a good ground. See if we have any continuity. Do you see it? We hear the beeping sound. The resistance is 0. It's because this wire is shorted to ground. If I go for CAN low, and again, as you see, I'm not getting any continuity right now because CAN low is not shorted to ground. So this is what we can do first of all to identify if one wire on the CAN bus is shorted to ground or not. And if I check the resistance between these two, CAN high and CAN low, I'm gonna get 60 ohms, the normal resistance for the entire CAN bus. Considering that we have two terminating resistors, the total resistance of the CAN bus should be 60 ohms. So this is the normal resistance. If these two are shorted to each other, you're gonna have way less resistance value over here, which tells you the issue. So right now that we know one wire is shorted to ground, we need to go for isolating the problem area step by step to find the issue. I explained this in one video, step by step. I explained how to isolate the problem area and how to find the issue. You can find the link for that video in the video description or on the channel. Using the oscilloscope, you can find out a lot about this. I'm gonna show you the waveform, the good one and the bad one, right now in a second. But very quickly, I'm gonna show you the joint connector that I mentioned earlier. So if you look at the wiring diagram very quickly, again, you see many control units are connected to the network through this joint connector. Here's the joint connector that I mentioned. So you see the joint connector, and at the back, if you look at the wirings, red and blue wires, they are for the high-speed CAN. So this is CAN high and CAN low, they are on the high-speed CAN. And these white and brown wires, they are for the low-speed CAN or B CAN that you saw on the diagram earlier. So this joint connector is gonna connect the network together. So these two are connected to each other, these are connected to each other through the joint connector. And for isolating the problem area, we can actually use this joint connector. So if I take the joint connector out, you should do this very carefully. This is the joint connector. So these pins are connected to each other from here to this point and from here to this point. So right now that we remove the joint connector, we can check the pins one by one from here. For example, if you find the CAN bus high and CAN bus low for engine control module here, you can actually check each wire from here, and that's going to be the network wiring of the ECM. I'm going to put this one back. Let's go for checking the CAN bus with oscilloscope in normal or shorted condition. So today I'm using MICSIG oscilloscope. This oscilloscope is specialized for automotive purposes. It's been a while I'm using this oscilloscope. It's quite nice. This oscilloscope provides 4 channels. I'm going to use channel 1 and 2 because we are going to read the waveform from CAN high and CAN low of high-speed CAN. The channels are here, so you see one channel is on. I'm going to turn on the channel 2 just like that. One end of the oscilloscope probe is connected to the oscilloscope. On the other end, I have these two. This is going to go for picking up the signal from the CAN bus, and this is for a good ground. I'm going to use a back probe to insert it on CAN high and CAN low. I put the channel 1 on CAN high and channel 2 on CAN low. And I'm going to do it on the OBD2 connector. Those pins that I showed you, pin number 6 and 14, they are for the CAN high and CAN low. I'm going to insert these ones there, and I provide the ground. Then we turn the ignition switch on to read the waveform. The waveform that we get at the beginning is a good waveform. Then I make the short to ground again on CAN high, then on a CAN low to see what's going to happen. I'm going to turn the ignition switch on right now because I inserted the test probes on pin number 6 and 14. And then after turning the ignition switch on, I'm going to click on the auto set to see how this oscilloscope is going to set the waveform for us, because of course we have different adjustment in here. Okay, so this is what oscilloscope is showing us, CAN high and CAN low. I can bring this one down a little and this one up. For having a bigger waveform, a little bigger waveform, you can adjust the voltage in here. So basically you can adjust the time setting here and the voltage setting there. If you change the voltage setting, you're gonna have a taller or shorter waveform, and using the time setting, you're gonna have more or less number of signals. If we increase the voltage here on channel 2 to 1 volts and channel 1 to 1 as well, you can adjust the time here, or you can go one by one. If I tap on this one, I'm gonna have less number of waveforms. If I show you more number of waveforms, just like this. This is the waveform that this oscilloscope is showing to us in normal situation of the CAN bus. This is a CAN high and this is a CAN low. As you see, they are completely symmetrical. So for example, if I move the CAN low here, you see that these two are completely symmetrical. We need the waveform on each one of them. We need a symmetrical waveform, and the voltage range is important as well. On CAN high, the voltage changes between 2.5 to 3.5, and on a CAN low, it changes between 2.5 to 1.5. So this is the vertical cursor for reading the voltage. The color of the cursor shows which channel you are checking right now. So you can actually change the channel from here to channel 1. The cursor already changed to yellow. It means we are actually checking the channel 1. So this is one line, this is one line. I can grab it and move it down here. And this one, the base voltage. You can read the voltage right now here, Y1, which is the maximum voltage, is 3.5, and Y2 is 2.5. So as I mentioned, CAN bus voltage changes between 2.5 on the base to 3.5 at this point. This shows the normal voltage range. If you check it with multimeter, you're gonna get something different because your multimeter is not fast enough to show you the voltage change. So it's gonna show you something around 2.6, 2.7 on CAN bus high. And if you change the channel to channel 2, and if we do the same thing on channel 2, I'm gonna grab the cursor and this one right there. It's very responsive. I like it how fast it works. So you see the Y1 in this case is the base voltage on the CAN low, it's 2.5, and the minimum voltage on CAN low it's 1.4. So we need a nice symmetrical waveform with good voltage range. What's gonna happen if there is any issue? This is a good waveform. What happens if there is a short ground on the CAN high, as I mentioned before? So I'm gonna turn off the cursor. I make the short ground on the CAN high again, then we read the waveform. I made the short ground on the CAN high. Let's run the waveform. So as you see, waveform is gone. Both on CAN high and CAN low, waveform is gone, and if you check the voltage here is very close to 0. So this is what's gonna happen when you check the waveform with oscilloscope. If there is no waveform, most likely the CAN bus high and low, they are shorted to each other, or one of them is shorted to ground. If there is no waveform at all, most likely the ground is on CAN bus high. I'm gonna stop the waveform. Now I'm gonna change the short ground from the CAN high to CAN low. Then I run the waveform again to see how waveform is gonna look like when there is a short ground on the CAN low. Okay, I changed the short ground to CAN low, and I'm gonna run the waveform now. So as you see, what happens right now, there is no waveform on the CAN low. CAN high is giving us some waveform, but we can tell that this waveform looks very abnormal. And if we go for checking the voltage again, CAN low is showing us something very close to 0. But on the CAN high, see what we are getting right now. Again, remember that I made the short ground on CAN low, and it's affecting the CAN high as well. So you see the voltage already changed. At Y2 at the base that we should have 2.5, we have something very close to 0, 138 millivolts, which is very close to 0. At up here that we're supposed to have 3.5, we have almost 3 volts. So using the oscilloscope, we're not going to only read the waveform, we need to analyze it as well. Because here we have the waveform, but when we analyze it, when we check the waveform voltage, we see that it's not normal at all. Because the CAN low short to ground is affecting the CAN bus high waveform as well. This is actually how we can use the oscilloscope for diagnosing the network. What about CAN timeout? I have already explained a little about the CAN timeout in the previous section when there was CAN bus off. The other control units which could not communicate with one of them, they all set CAN timeout with ECM. Same story here. We are looking at the very same diagram. The type of fault code that you will get is going to be lost communication with one control unit. One control unit will be mentioned in here, and CAN timeout with that control unit. So these are two different type of fault codes that you will get. It's really important to remember that this fault happens if the required message is not received for a certain period. Again, we are looking at the ECM. ECM has some issues receiving the data from transmission. Just imagine that we have two separate control units for engine and transmission. If ECM has difficulty to receive information from TCM, is going to set this fault code for us, U0101, lost communication with TCM, or CAN timeout TCM. So it means in this case, you will have communication between scan tool and ECM is reporting the issue on TCM. If we look at the diagram again, of course here you don't see any TCM, because if this car is equipped with automatic transmission, the TCM control unit will be integrated with ECM. That's why down here you have ECM for a manual transmission car and PCM for automatic transmission car. So that's why you don't see TCM in here. But just imagine, look at the instrument cluster, which is connected to the high-speed CAN as well. If instrument cluster is not responding properly to the ECM, ECM will set a fault code for CAN timeout with instrument cluster. So it means there is no communication between ECM and instrument cluster. Look at the CAN bus wires between the ECM and instrument cluster. ECM has two wires connected to the joint connector. From here goes all the way to instrument cluster. So what we have right now is the communication error between ECM and instrument cluster. You may have this fault code on some other control units on the CAN bus as well. And because all other control units are responding to the CAN bus, there's no short to ground or short to each other on the CAN bus. For checking the network, you can simply find these two wires, which are the CAN bus wires between the instrument cluster and the joint connector, to check them for any open circuit, for example. I'm going to show you how to do it today, because the issue could be on here or even on the connector on the instrument cluster. I'm going to show you how to find the wires and how to perform that test. Let's just imagine that the CAN timeout that the control units are giving to you is CAN timeout with instrument cluster. So it means the instrument cluster is not responding, is not communicating with other control units. If we look at the wiring diagram one more time, you see that instrument cluster is located right here and is connected to the network with those two wires through the joint connector. So it means the first option, of course, is going to be to check the connector on the instrument cluster. But for making sure if there is any open circuit or damages on the network wiring on the instrument cluster, the best way for isolating the problem area is to check those wires between the joint connector and instrument cluster. Here is the joint connector. You see the wiring diagram at the same time on the screen. So I'm going to take the joint connector out again. On this side, we can of course check the CAN high and CAN low. If we focus on the CAN high, pin number 4 on the joint connector is for the CAN high of instrument cluster. So look at the joint connector details. You see the pin number 4. This is actually pin number 4, which is the CAN high for instrument cluster. This one, this red one, I can insert the test prop from there. So this is for the instrument cluster CAN high. And the other end of this CAN high is connected to the instrument cluster, as you see on pin number 29. So you see the pin number 29 on the instrument cluster connector too. So here is the instrument cluster connector. If you look at here, these two wires which are twisted, they are CAN high and CAN low. So we are looking for pin number 29. If you look at the connector like this, based on what we have there, so it's just right here. And if you look at the back, this is the CAN high, this red one. You see the red and blue, they are next to each other. The blue one is CAN low and the red one is CAN high. I'm going to insert the probe right there. And now we can go for testing the wiring. On multimeter, I select continuity. One end of the multimeter right here. And the other end is going to be on that test probe that I inserted on the joint connector. and see if there's any continuity. You see, there is continuity and resistance value is 0 ohm. This shows that the wire is connected, there is no open circuit. So if you do not get any continuity or resistance value is really high, it means you already found the wiring, because you are checking the CAN bus wiring between here and the joint connector. This is how instrument cluster is connected to the network. And if I go for CAN low, I can just switch this one from here to CAN low, the wire next to that. And on the joint connector, I need to go for pin number 15. I switched the test probe on the joint connector on pin number 15. I'm pretty sure it's easy for you guys to find out. And here it's on the CAN low. So let's read the continuity. Again, we have the continuity and it's all good. So this shows that the CAN high and CAN low, they both are connected properly to the network and there is nothing wrong with that. If you didn't have continuity or you had any abnormal measurement, it shows you that that piece of wiring is open or there is high resistance in there, which is causing the issue. So you can focus on it and fix it. And that's the reason that control units are giving you the fault code as CAN timeout with instrument cluster. But the last type of error that we can diagnose on the cars, which is related to the CAN bus, is CAN message error. I'm going to show you one example about one fault that we actually had on a Ford Kuga. I recorded a video from the scan tool and I'm going to show you what happened. Message error is a DTC generated when a controller receives required signal in error. Just remember the difference between this one and timeout. On the timeout, there is no data reception. For example, TCM is not getting any information from ECM anymore. That's why TCM sets a CAN timeout fault. But in message error, we have the data reception, but in error. It means there is some information delivered, but it's not accurate. Message error DTC is generated by reception controller. Just remember this one. By reception controller, one controller is asking the information from another control unit. The second control unit responds, provide the information, but this information is not accurate. So in this case, the reception controller is going to set a fault code. Transmitting controller does not have message error DTC. For example, just imagine that transmission control module requests the information of engine RPM. ECM will receive the engine RPM from crankshaft position sensor and is going to share it with transmission control module. If this information is delivered properly, all good. But if transmission has received the required signal in error, it's going to set a fault code. And the fault code is going to be something like this: invalid data from ECM. Sometimes it's not going to point exactly to the engine RPM, but if you check the ECM with a scan tool, you may get some fault code related to the crankshaft position sensor. So once you fix the crankshaft position sensor, that fault code in ECM can be erased. And of course, the other faults on the other control units will be erased as well, because there is no invalid data anymore. Look at one example that I actually had. This car was a Ford Kuga. We had a couple of fault codes in ABS and a couple of other control units. For example, we had fault code in cruise control modules. And when we read the fault code, look at the fault code. It's U0418, data invalid from braking system. So it's referring to a data invalid which was delivered from the ABS. And if we go for front distance sensing module, let's see what sort of fault code we have in here. Again, invalid data received from ABS system. So two control units are reporting that ABS is sending a wrong information, but the data is received, but wrong data. Let's go for the ABS, see what sort of information we have in here. We're going to read the fault code on ABS. And when we read the fault code, we have several faults for rear left speed sensor. So rear left speed sensor was faulty in this case. That's why ABS was delivering incorrect data to other control units. And the moment that we replaced the ABS sensor and we erased the fault code on ABS, everything was back to normal with no issues. So sometimes the fault code could be showing a network issue, but when you check on the car, there is no network issue actually. the problem is from the source. You fix the source, the network fault code is going to go away as well. Alright guys, so this was the video for CAN bus diagnostic. I hope you enjoyed the video. If you are interested to learn more about automotive network, of course you can find many other videos that we have on the channel, and you can find our online courses in the video description. Thank you very much for watching. I hope you enjoyed the video.